Hello, it's Dr. Harris, and we are continuing our work through Chapter 7 in our Statistics Math 111 course. We've introduced how to uh, find confidence intervals for single means, and we've talked about t-distributions, looked at the sampling distribution of the sample mean, and now in this video, we're going to talk about uh, hypothesis testing with uh, single means. So let's do it. So recall that we're going to read a scenario and form competing hypotheses. Our null hypothesis is going to be a statement of equality. Our alternative hypothesis is going to be a statement of not equal to, and we're trying to judge whether or not it's the evidence that we've collected from our sample forces us to say that our null hypothesis is incorrect. So we're either going to reject the null hypothesis in favor of the alternative, or we're going to fail to reject it, saying, well, there's a difference, but it's just not large enough that it couldn't have happened just by chance. And so this time our hypotheses are going to involve single population means. So we're going to start by looking at the scenario that we were studying in our previous slideshow/video from page 259 in our text. We're looking at investigating the mean number of years of piano lessons taken by children in a particular small city. And so we can go back and take a quick look at that problem just to make sure that we're on board with it. Let's find it right here, page 261. Georgiana claims in a small city renowned for its music school, average child takes, we're saying, 5 years of piano lessons. We're striking the words less than. In our random sample of 20 children, the mean was 4.6 years of lessons, standard deviation 2.2 years. In the previous video slideshow, we looked at part B, finding a 95% confidence interval. And now we're going to be looking at a hypothesis test, trying to see if Georgiana's claim is reasonable or not. And then once we get that done, we'll be able to look at actually part C as well. Okay, so what are our competing claims about mu? Last time we saw that mu is the mean number of years of piano lessons taken by children in this city. So let's think about it. If Georgiana believes that it's 5 years, we're testing to see if it's 5 years or not, then our alternative is going to be that it's not 5 years. And so here are our hypotheses. The null hypothesis is that mu is equal to 5. And our alternative hypothesis is mu not equal to 5. And I've translated both of these equations, the equation and inequality here, into words. So we're trying to judge from the data that we've collected in our sample whether or not the null hypothesis is reasonable or not. So just recalling, our sample mean was 4.6. Our standard error is the sample standard deviation divided by the square root of the sample size, which turned out to be a number a little bit less than a half. And in order to find the p-value, we're going to, as you recall from our last video, we're interested in t-scores to help us find probabilities involving t-distributions, which we have to do because we're using the sample standard deviation rather than the population standard deviation, which is unknown. And so we're going to use a t-score to help us find the p-value. So our t-score is the observed value minus the hypothesized mean divided by the standard error, 4.6 minus 5, and we divide that by the 2.2 over the square root of 20, and we get negative 0.813 to 3 decimal places. And so let's remind ourselves that a p-value with a two-sided alternative is the probability that we got data as extreme or more extreme than what is suggested by our null hypothesis. So if our t-score is negative 0.813, we're 0.813 away from 0, the center of a t-distribution on the low side, and so we need to extend it to 0.813 on the high side. And so we're going to enter C of negative 0.813 to 0.813. We use a region of outside because we want to the likelihood of being as far away or farther. We had 19 degrees of freedom. Remember, our number of degrees of freedom is one less than the sample size. And we're going to have a graph here as well. Here is our result. We can see that the area outside the region from negative 0.813 to 0.813 is about 42.5% of the total area underneath the t distribution curve. So our p-value, to 3 or 4 places, 0.426, rounded to 4 decimal places, 0.4263. So let's interpret that using a sentence. If our null hypothesis is true, under the assumption that children in the city do average 5 years of piano lessons, the sample selected gave us a mean such that getting it or one farther away from 5 would occur about 42.5% of the time. So we usually compare to the 0.05 standard. And so comparing 0.426 to that, it's much greater than 0.05. And so recall that when our p-value exceeds our point of comparison, then we fail to reject the null hypothesis. And we're going to say, well, the null hypothesis is not unreasonable. So getting 4.6 from 20, an average of 4.6 out of 20 students, far below 5 isn't that unusual if the true mean were actually 5. Okay, so that's just reminding ourselves about the process of hypothesis testing there. We state hypotheses, we do some calculations, we enter those calculations into a probability calculator to get our p-value, and then we make a decision based on the p-value. So that's part A, running a hypothesis test. We're failing to reject the null hypothesis. But now let's look about part C, where we want to draw the connection between the confidence interval and the result of the hypothesis test. So in our last slideshow, the 95% confidence interval for the population mean was about 3.6 to 5.6. And notice that 5 is in that confidence interval. Our null value is in the confidence interval. And we failed to reject the null hypothesis. Mu equals 5. These things should not surprise us based on what we saw back in chapters 5 and 6. So when the null value is in a 95% confidence interval, we fail to reject the null hypothesis against the two-sided alternative. And it's important that we did our comparison to 0.05. If the null value is not in the 95% confidence interval, that's a sign that we're going to reject the null hypothesis in favor of the two-sided alternative. And again, that's assuming we compared our p-value to 0.05. I said that's our default value. We would specify in advance if we were going to use some other point of comparison. That's what we call the level of significance. In our textbook, in other places, you might see me refer to this as alpha. Alpha is the level of significance that we compare our p-value to. And so if the p-value is above the level of significance, we fail to reject the null hypothesis. If it's below the level of significance, we reject the null hypothesis. Let's translate that. If we were doing a 90% confidence interval, that would mean that our level of significance is 0.1, 10%. So we would subtract, to get the level of significance, we subtract our confidence level from 100%. So 100% minus 90% gives us 10%, translates to a 0.1 level of significance. 100% minus 95% is 5%, which translates to a 0.05 level of significance. So the corresponding statements here with a 90% confidence interval, if our null value was inside a 90% confidence interval, that would signify that we're going to fail to reject the null hypothesis against a two-sided alternative using the 0.1 level of significance. And if the null value is not in the confidence interval, then that's a signal that we would reject the null hypothesis in favor of the two-sided alternative at the 0.1 level of significance. There's a corresponding statement for 99% confidence intervals, and we'll be touching on that as we go through our work here. So I'm going to ask you to do some work now. This is our parking garage example. The sample mean from 60 days worth of data was $126 in parking fees, standard deviation of $20. The consultant said that the city would average $130 on weekdays on average. And so we want to look at the question, does the data that we've collected indicate that the consultant made a mistake, that 130 is not a good choice for the population mean value. So I'm going to ask you to do the work here, form your hypotheses, compute your t-score based on the sample mean, and use PTGC to find the p-value and draw your conclusion. Write this up, and we'll talk about this in class. So I'm going to try to get you to get some practice on this on your own. So we want to be able to do those things for hypothesis tests, quote, by hand, where we're going to compute the t-score, put it into PTGC, and you get the p-value to make our decision based on that. But as we saw in chapter 6, we have these one-stop shopping commands in RStudio that do confidence intervals and hypothesis tests all at once. For this chapter, our command is going to be t-test-gc. And we can use this on preloaded data, or we can use it on summary data. So we've got a summary data example with the piano lessons. So let's see how t-test-gc works in that case. We give it a mean, and we give it a standard deviation. We give it a sample size, and we give it a null value. So mean, standard deviation, and mu are those things. So we just give it the summary data. We tell the alternative is going to be 2 dot-sided. We indicate where the confidence level was, 0.95 up front, and we're going to look at a graph. So I'll go ahead and run this in RStudio. And we'll see that we get a huge raft of output. So here we go. There's our command. Here is all our output. And so there's so much here that it's going to take a few slides to sort this all out. But let's see what we've got here. So first thing, we just get our summary data spit back at us, the mean, standard deviation, sample size. Here is our sample mean, and there's the calculation of the standard error. This does match what we computed before, the standard deviation divided by the square of the sample size. Our confidence interval calculation is done for us. This matches what we computed earlier. I guess it's maybe off a little bit in the second decimal place, but this is really, really close. And here are our hypotheses. Remember that the exclamation point means not, so mu not equal to 5 is our alternative hypothesis. Here's our test, our t-score, our degrees of freedom, and there's the p-value, which matches what we got earlier from PTGC. So this is a really good fit for what we've done by hand. It's closer overall than what we got back in chapter 6 with prop test GC or binom test GC. So again, our p-value is much bigger than 0.05, so we're going to fail to reject the null hypothesis. And finally, we do get the graph, the same graph that we got out of PTGC. Okay, so now let's look at an example where the data is actually already loaded into RStudio for us. I think at the beginning of chapter 7, we looked at this question: do students at UC Davis get average 6.5 hours of sleep per night? And I think we set up the hypotheses back then. Mu is the mean number of hours of sleep for all students at UC Davis, and we have our null and alternative hypothesis, an equation, and an inequality. 6.5 is our null value this time. So remember, before we proceed, we want to make sure that our data is relatively bell-shaped, and we do a density plot here. This really looks nice. So it's very, very close to bell-shaped. Nothing really much in the way of outliers on either side. So it's nice and symmetric. We should feel pretty good about proceeding in this case. If we're going to do the by hand computations, we need to apply favestats and get our output. So our mean value is 6.93. Our standard deviation is 1.71. I'm rounding to 2 decimal places. And so we need to think about how many degrees of freedom we're going to use for our confidence interval. That's where we're going to start here. We're going to actually for our hypothesis test. How many degrees of freedom are we going to be using? Actually, we are doing a confidence interval first. Let's do a 99% confidence interval. So let's remind ourselves, number of degrees of freedom, we'd expect to use 172 degrees of freedom based on our sample size. But if we go to our table in the back of our book, we scroll down to our second page, and we see that 172 is not one of our options for degrees of freedom. So we have to figure out, well, what am I going to do when I don't have that information from the table? And the thing we're going to do is we're going to always round down to the highest value that's below the actual number of degrees of freedom. So if we round down here, the closest one below 172 is 150. So if we're doing a 99% confidence interval with degrees of freedom 150, remember our two-tail area this time is going to be 0.01. 100 minus 99 is 1. 1% converted to a decimal is 0.01. So we'll be out here in the fifth column this time, and we're going to go down to 150 degrees of freedom. And so 2.61 is going to be our value of T star for our confidence interval. So we're going to use 150 degrees of freedom. We get 2.61 for our value of T star. And so remember, for a confidence interval, it's the sample mean minus T star times the standard error to the sample mean plus T star times the standard error. 1.71 divided by the square of the sample size is our standard error this time. We get 6.59 to 7.27. So we would say we're 99% confident that the mean number of hours of sleep obtained by UC Davis students is somewhere between 6.6 and 7.25 hours, speaking, rounding just a tiny bit. So this is just a good reminder of how we do our confidence interval. Now let's do our hypothesis test by hand. We need to find the t-score. And so the t-score is the observed mean, 6.93, minus the null mean, 6.5, divided by the standard error. And we get about just a little over 3.3. So to find our p-value using PTGC, remember, we're going to look at the region outside negative 3.307 to 3.307. Again, p-value is the probability of landing as far away as our data did or farther, and that could be as far away on the low side as well. So what does PTGC reveal? It's a very small number, 0.00115 to 5 decimal places. Here's our sentence of interpretation. If the null hypothesis is true, that is, if students at UC Davis do indeed average 6.9 hours of sleep, our sample yielded a sample mean such that it or one farther away, it should not be higher, it should be farther away, would occur only 0.1% of the time. And that's not 1%, that's 0.1%. 1/10 of 1%, roughly 1 out of every 1,000 times we would run an experiment. We'd expect to see a t-score this far away or farther, if the null hypothesis is true. So if we were to compare it to 0.05, we would certainly reject it. If we were to compare it to 0.01, remember if we did a 99% confidence interval, that might be indicating that our value for alpha, our significance level, is 0.01 this time. And so we would reject the null hypothesis in either of these cases and conclude that the students at UC Davis do not average 6.5 hours of sleep, and certainly it seems like likely more than that. Okay, so if I wanted to rerun this using our one-stop shopping command, we don't have to enter the summary data. We just tell it what the variable is. It was tilde sleep. Remember that sleep was capitalized. We give it our data set name, UC Davis 1. We're going to set the confidence level to 99%, 0.99, and then we give it the null value and the alternative. We could include graph equals true here as well. So again, we do need to provide the confidence level and the null value and the alternative hypothesis, but we don't give the summary data this time. We just say variable name and the data set. Here's a summary of some of the results that we got. The confidence interval turned out to be 6.6 to 7.27. That's slightly different from what we had prior. I'll explain why in just a second. Our test statistic is 3.355. uh, a little bit different again, and degrees of freedom this time. And here's why the test statistic is a little different, and why our confidence interval is a little bit different. It used the actual number of degrees of freedom. Our studio has access to basically the values of t star for all possible degrees of freedom. We had to round. We used a slightly bigger number than we would have had to, and so we're going to get a slightly we would get a slightly smaller test statistic, a slightly different confidence interval, and a slightly bigger p-value as well. Um, if we use the rounded down degrees of freedom, so t-test GC gives us the more accurate responses, and so we still see that our p-value is well below 0.01, and so we would do indeed reject the null hypothesis. Okay, so we want to give you a chance to do some more work. Consider the variable exercise in the data set UC Davis 1. And we want to ask, do the data collected provide strong evidence that the mean number of hours of weekly exercise from UC Davis students is 5 or different from 5? So I'm going to be asking you to check the commands or check the conditions. So we need to think about what we would do to actually verify that we should proceed. Think about what we did earlier with the previous example involving sleep. Let's state our parameter mu in words. Let's form our hypotheses, and then let's do the work. So again, you do this. We'll talk about the answers in class, and we will go from there. If we want to use t-test GC, again, give the variable name, the data set name, our null value, and our alternative. This time I've got graph equals true. So you do all this, see if your by hand work compares to what happens of t-test GC, and we will go from there. So again, giving you a chance to fill in these things. What's our p-value and what's our decision? So just giving you prompts on the things to think about to do the work here, and you can do that, and we will be talking about these results in class. Next up, our next video is going to involve how to handle the case when we're talking about the mean difference between paired data.